Okay, hello everybody. Thank you for joining us in our second Saphir regular webinar of the year. And today I'm really happy to have a artificial intelligence and machine learning expert for particle physics, Gregor Kasieczka. I hope I pronounced that correctly.
Gregor, almost, very good.
Almost. Gregor is currently with us. He's from the University of Hamburg. He has wide experience in experimental particle physics as well, as part of a member of the CMS collaboration at the LHC at CERN. And today he will tell us about new tools for AI-based discovery in particle physics. Gregor, thank you so much for accepting our invitation, and please go ahead with your seminar.
Yes, thank you so much for this invitation. It's a bit in the evening in Hamburg now, and I did my very best to be here because by accident we planned a 100-mile bike trip, but we got back in time, and I'm refreshed and excited now to tell you a bit about what we're doing with machine learning. Okay, so I think we have quite an expert audience on particle physics, so we can zoom right in from our all everyday experience. This is a nice culinary treat from Germany. It's a pretzel with butter inside. All the pretzels I've had in the US are way too dry. I don't know if you have nice pretzels in Chile, but if we zoom in by 14 orders of magnitude, we get to the standard model of elementary particle physics. And what we try to do in experimental particle physics is really to try to understand nature at this most fundamental level and to uncover the behavior of these particles. And we're using, of course, the largest and most precise scientific instruments ever built for this endeavor. And just to counteract a bit the public perception, in 2012, it was announced the discovery of the Higgs boson, and it was a big celebration, and it was awarded with the Nobel Prize. And now sometimes people say particle physics is over. But of course, that is extremely wrong, as you, of course, know, and much remains to do. And the way that is usually this is usually put is that we can divide the things that have to be done into two broad categories. On the one hand, measuring the behavior of the standard model even more precisely, and of course, especially understanding the behavior of the Higgs boson is here of great interest. And this is really the focus, the primary focus of my research, is looking what is beyond the standard model. And since this is a seminar on AI in particle physics, let me just give you a slightly different summary of the overall business before we hone in on the specific question of AI-based discovery. So one of the exciting things about particle physics is, of course, that it's a first principle quantum theoretical model, the standard model underpinning all of this. And based on the standard model, we can, on the one hand, this is the left pass, run collider experiments that produce 40 million collision events per second in these complex detectors that each have on the order of magnitude of 100 million readout channels, so producing immense amount of data. We don't save all 40 million events per second, we just save around 1,000 per second. We'll come to that towards the end of this talk. And secondly, in addition to these vast amount of collision events, we also have a substantial amount of simulation efforts to produce fake events, but of course they're no simple fakes, they're very sophisticated because based on this high quality theory, we can simulate to great degree of fidelity both the theoretical processes and also the interactions of the produced particles with these complex detectors. And all of the things that we're talking about are close to impossible without simulation to either design experimental studies or to use them also in the analysis of these data. And both the simulations and the experimental data are then jointly processed by some complex reconstruction software that turns the low-level energy deposits and measurements from the detectors into high-level understandable physics objects like reconstructed electrons, muons, or reconstructed jets. And then in the end, we pipe all of this through some sophisticated final analysis here, for example, a plot from the discovery of the Higgs boson. Now, if we ask were machine learning or AI, and I'm going to use these terms pretty much interchangeably throughout this presentation, if we ask where these tools are employed in particle physics, then nowadays the answer is pretty much everywhere. Sometimes it's on the order of first tests and exploring these techniques, but in many cases, it has become a working horse, as we'll see in some parts of this presentation. Now, since all these areas would be a very long and boring talk, I gave one that tried to cover everything something like 10 days ago, and that's not so exciting as trying to focus on one specific path. And the path I would like today is seeing how we can really use machine learning and AI to enable the next round of scientific discoveries at the LHC. And when I say enabling discovery, to set the stage properly, let's go back a bit in time, around 40 years to 1983. And we see here on the left-hand side, a collision event recorded by the Underground Area 1 UA1 detector at the CERN superproton synchrotron. So you see, the picture is very similar to what we know from modern particle collisions, but of course the detectors have less resolution, and the color scheme back then was just way nicer. And we're looking here specifically at the road to the discovery of the C boson. And we have here the production process of the C boson. So we have quark-antiquark annihilation going into a C boson, decaying into an electron-positron pair. And if we are able to properly reconstruct the electron four momenta and calculate their invariant mass, we can plot the invariant mass. This is shown on the histogram on the right-hand side here. And going from top to bottom are just increasingly tight reconstruction criteria. So essentially making sure that we really properly reconstruct electrons as a combination of some energy deposited in the calorimeter and some track pointing to it. And if we do that, it's nice. Everything back then was far cleaner. It's a background-free process where in the final selection, we have 4 events clustering around the mass a bit below 100 GeV. And this was really the first direct hint or actual evidence for the presence of the C boson. If we fast forward now around 30 years, and of course the W boson and the C boson were awarded with the Nobel Prize for Rubia and van der Meer in 1984. If we fast forward around 30 years to 2012, we have now a much more sophisticated looking event display. This is from the CMS collaboration, but one of the channels for discovery follows a very similar track. So in the bottom, we again have the Feynman diagram. We have gluon production. We have some loops. We don't care about them here, but the important thing is we have Higgs boson produced that in the channel we're looking at here decays into a pair of photons. And like we did with the invariant mass of the 2 electrons to recover the C boson, we can look at the diphoton invariant mass looking for the Higgs boson. If we do that, we see, of course, one big difference is that nowadays most events are background. These are either misreconstructed photons and of course also standard model processes that produce pairs of photons with a very tiny signal on top. And if we want to dig out that signal, well, we can have a first step with machine learning, and it was done as it was done in the discovery of the Higgs boson. Actually, what we can do is divide the events that we record into something like 25 different categories, sorted by their purity, sorted by how well we reconstruct the individual photons, and then use simulation-based, here it comes in that we have access to these nice high-quality simulations, use simulation-based information, expecting where how much signal should be in each of these categories to just enhance the presence of signal. And we can see nicely now that we enhance the Higgs peak in the diphoton invariant mass, or we can use this information in the statistical analysis that led to the discovery of the Higgs boson. So also the Higgs boson was awarded Nobel Prize for the theorists predicting it in 2013 for the Higgs mechanism. And of course, we're still shocked by the passing away of Mr. Higgs. Good. So brief summary so far. The point I would like you to take away is that resonances at the well-defined mass are very clean and beautiful discovery signatures. Also, sorry, this is in German below, but this is a saying, früher war alles besser. Back in the days, everything was much better. And you see now this is a plot with a bit more statistics, but it's still essentially background-free observation back then. Then, second takeaway is that machine learning allows us to enhance a small signal in the presence of large backgrounds. And what I'm going to talk about for the next 40-ish minutes or so is how modern machine learning techniques can enable the next big discovery, and the tricks we need to play to get there. And this talk is structured into 3 pieces. I will first talk about supervised classifiers, where we know what we want to look for. Secondly, about anomaly detection. And then if we have time, I'll briefly touch on foundational models. Don't worry if I spend lots of time on anomaly detection. The foundational models part is really brief towards the end. Okay, so how can machine learning enable the next big discovery? And the ingredient that we're using is machine learning, or AI. And this is not a talk that dives into the details of network architecture. We're not going to talk about hyperparameters and numbers of layers and such things. We're just, for the most part, going to see machine learning, and specifically deep neural networks, as a very general function that has a bunch of tunable parameters, and we're using iterative gradient descent-based approach and training examples that we typically obtain from simulation to fine-tune this function to the specific task that we're trying to solve. We're going to think a bit how different symmetries that we can put into the construction of this function enable it maybe to learn better. But for any more details on machine learning, of course, I'm happy to answer any questions that come up in the discussion. So how can machine learning enable the next discovery? And we're first looking at supervised classification. So we can pivot a bit, and we go back in memory to thinking of the discovery of the C boson, but now we're not looking for the C boson, but for theoretically somewhat motivated heavier cousin of it, sequential additional gauge boson that we can call the C prime. So essentially a heavier cousin of the C boson, and we're specifically looking for a decay of the C prime boson to a pair of top quarks. In general, we don't know the mass of this resonant particle. Of course, the range is being constrained, but we still need to look for all possible masses. But we can assume that it will, for example, decay to a pair of top quarks. And specifically, we assume it decays to a pair of reasonably boosted and hadronically decaying top quarks. So top decaying into a W boson and a B quark, and the W boson subsequently decaying into 2 additional quarks. Which brings us to the problem that top quarks are more complicated than electrons. So we have here a view of a top quark into 3 jets coming towards us. And the name of the game is really how we can use AI for this top quark identification. And whenever we think about using machine learning techniques to solve any technical problem, the first question is how we can represent the data. And after a couple of years of trying different things, I think we have a reasonable consensus point that the simplest representation that is useful for particle physics data is to treat each jet or each event as a set of k-dimensional vectors, where k could, for example, be 3, a spatial position in the eta phi plane of the detector, and an energy, as we see here. So we have hits at different points, and the length of these bars correspond to their energies. And a priori, we don't know the ordering of these things. That's why we say it's a set. So we could impose some ordering, but there is no physically motivated way to order the different particles in the jet unless we have access to the clustering history. And I talk here about 3-dimensional vectors, but of course, we can also increase the dimensionality and include such information as the relative fraction of energy deposited in different parts of the colorimeter, or something like track-based information like a displacement. And we want to use these so-called point clouds, where each point cloud corresponds to 1 jet, to tell if a jet is a top quark or not. And the next couple of pages of results I'm going to show are based on the so-called landscape dataset. So from the paper, The Machine Learning Landscape of Top Taggers. And you can think of this really a bit like the MNIST dataset for machine learning. So it's a bit old. It doesn't have as many examples in this high resolution as newer datasets, but it's very useful because many things have been tried on it. So to be specific, it contains around 2 million simulated examples, top quarks versus light quark or gluon jets. And the simulation, as I said, is done on a relatively simple level. So this is Pythia for the physics process and Delphis as a detector simulation. And as an input, we only store around 200 particles per jet with 3 features per particle. So the energy and the direction. And the important thing is, of course, that we have perfect class labels. So because we know for each example whether we simulated a top jet or a light quark or gluon jet, we can use this information to train a machine learning algorithm in a supervised way. The results I'm going to show will be looking at in a 2D plane. Let's start with the horizontal axis. The horizontal axis is the number of trainable parameters. So essentially the complexity of the neural network. It's much easier to count parameters of a neural network than it is to benchmark 20 different algorithms on the same compute hardware. So it's a useful proxy, even though in detail, of course, there might be other operations that factor into the overall compute cost of a given algorithm. And on the vertical axis, we have a quantity called R30. It's it's essentially assuming a selection criterion that allows 30% of the true top quarks to pass as such. So if you look at the distribution of the output, we place a cut value. So 30% of the true top quarks are going through. And then we look at the inverse of the fraction of the amount of background. So of the falsely S-top identifies light quark and gluon jets. So it's a rejection factor, and the higher the rejection factor for the background, the better for us. Good. So with this information, let's look at some results. And I've now populated the table with all results I'm aware of for this data set. Don't worry, we're not going to go through all of them, but I want to highlight a few interesting results because it allows us to understand a bit better what is going on in this area. And the first thing we've highlighted is in a sense stupid, because this nice realization that we can best represent jets as point clouds of particles was not something we started with. So the machine learning algorithms that were popular in around 2017 were image-based techniques, something like ResNet or Image, that were really just algorithms that just outperformed humans for the first time on any interesting task. And of course, physicists went there and tried to use these things for top tagging by just projecting these point clouds onto the surface of the detector. This gives you a very nice 2D pixelated image. And it's not entirely stupid to do that, because the one thing that these convolutional networks are very good at picking up is locality. Things that are spatially close to each other in the detector probably belong together in some meaningful way, like coming from the same parent particle. So this is something that convolutional networks pick up. They're also translation invariant. The downside is that particle physics images are typically fairly sparse. So most of the cells in an image are not filled because our detectors are high resolution and do not populate the entire space. But it's still not a bad thing to do. And you see for around 1 million parameters, you get a performance that somewhere lies in the middle of the pack. But with this, machine learning, or specifically deep learning for this problem, had started in earnest. Let me just go through 2 other chains of developments. So the first is, the first idea is if we really use these point clouds and their permutation invariant nature, so that we don't know what's the correct order for the point cloud, and just use this to structure a network architecture. This is called particle flow or energy flow networks. And the nice advantage is we put in some symmetry property. We use the physics the way it should be. It's fairly cheap in computation, but we also see it's physically not very powerful. What we can also do is realize what we've lost by just looking at this symmetric thing. And what we've lost is, most importantly, a concept of locality. So this point that things that are close together in a spatial way should be more relevant for each other. And the big breakthrough was this idea of using graph-based network message passing graphs, where one first constructs a graph representation of the input data, essentially adding explicitly the information which particles are close in space to which other particles, and then having a network architecture that lets particles that are close to each other talk to each other. And this, you see, adds a bit of complexity, but gives us a nice step up of something like 30% in performance. And the latest realization was that the attention mechanism that learns which neighbors are relevant for each other, so essentially going one step further than graph-based things and really learning which relations are important, using essentially the same technology that underpins all these large language models. So attention-based transformers gives us, well, interestingly, gives us no increase in performance compared to ParticleNet, more or less, at the cost of many more parameters. So this is going from ParticleNet to ParT. Okay, this is interesting. And the reason for this lack of improvement in performance is that transformers are fairly hungry in terms of training data. So what Hui Lin and his collaborators also did was to pre-train this algorithm on a much larger data set, the jet class data set with 100 million examples, and then fine-tune it. So essentially just retrain the weights on the 2 million top-tagging data set. And then we see the actual impact in performance from these transformers, because this party fine-tuned FT gives us a nice big improvement. Okay, let's close this review of top tagging methods with one last point. That is, of course, as physicists, we would like to have physics information include in the architectures. The most important physics information that we could be including is invariance under symmetries, and most importantly under the Lorentz group. So either under spatial translations, rotations, or under boosts, because up to some limit, it should not matter under which angle and from which reference frame a look at a particular arrangement of particles. It should always be either a top jet or something else. And there's a few techniques to include this symmetry equivariance in the construction of network architectures. And we see while these symmetry-based methods are maybe not the most strongest performant ones in terms of just raw authority, they do offer the best trade-off between performance in the sense of rejection factor and the number of parameters. So we see something like a Pareto frontier emerging here. Disco FFS is another approach, completely differently constructed, but also using physics-informed inputs. Okay, so to close this off, I'm not going to go into how we use these techniques on actual data. Let me just say that, of course, these methods are being tested and calibrated on data. And I think the one nice number to see here is that over 40 CMS publications currently cite the latest tagging publication by CMS. So essentially, we now have access to default tagging algorithms for TOPS, Ws, Bs, Higgs, and other particles that can be very easily used in any analysis that makes some assumption about what physics objects should actually be present in an event. Okay, this concludes a discussion of tagging algorithms. And of course, we ventured into tagging algorithms because we want to discover new physics. This plot here is the recent Morillon overview by the CMS collaboration on the results by the Exotica group. I know this is very hard to read, and I'm sorry for that. Just think of each of the colorful lines as one PhD thesis. It's not entirely true. These are different publications that look for different models of physics beyond the standard model. And the colorful bars indicate which mass scale for the assumed hypothetical particle has been excluded. So we have a bit of a problem. I mean, it's very useful to include large parts of the parameter space, and we learn something about it. But it motivates, in my eyes, the need to also try to look for new physics in a more model-independent way. And this brings us to the second topic, the topic of anomaly detection. And to get us all into the right mind frame for this, we have here a simple toy example that we're going to look at before we construct the specific physics application. This is a picture of the Golden Gate Bridge, just taken from Wikipedia. And as you can see here by the indicated generation frame, this is something we're going to plug into DALL-E in a moment, specifically DALL-E 2. So what I've done is I've defined a signal cutout region, as we would say in physics language. I've really just used the eraser tool to remove a bit of the bridge. And then I'm telling DALL-E 2 to interpolate the background to fill in the missing part of the bridge. And if you have sharp eyes, you see that this in-painted region is not quite right. It's a bit bendy. It has a bit wrong patterns. Some of the lines don't go the way they should. But in general, especially from afar, it looks like a credible picture of the Golden Gate Bridge. So we can now stick these two images into a machine learning-based classifier, the original and the interpolated one. And if the classifier is not very good, it's going to tell us it's the same picture. In other words, there is no anomaly here. In practice, just to avoid this misconception, in practice, we're going to not use individual pictures, but we're going to use distributions of pictures to train and evaluate the classifier. But this principle stays the same. Now let's imagine we had a picture where Godzilla is attacking the Golden Gate Bridge, as indicated by this little plushie here. If we had done the same thing, and importantly, and if we had cut out exactly the region where Godzilla is sitting, or a region close around it, and had interpolated it, then the classifier would have been able to tell the difference, because now these two images, the interpolated one that assume everything is behaving normally, and the real one, which has some interesting thing going on, are not the same anymore. And this is exactly the principle we're going to use to construct our anomaly detection technique. So what this will allow us is, let's look back at the previous assumptions we had. We didn't know the mass of the resonant particle, but we assumed it decays into a pair of top quarks. What this now allows us is that we say we don't assume the mass and the type of this new resonant particle, and we also don't know what particles it decays into. There's two assumptions we're actually making. It decays into a pair of new particles, and this is a pair of jets. So we can still look at the dijet invariant mass. And this is probably one of the most important frontiers and important things to still relax for this. But we at least got away the assumption that we need to know the type of particle something it decays into. So this we can also think of as resonant anomaly detection. And let's see how we can construct a useful anomaly score in this case. So let's look at this picture. We're going to assume we have one feature that the new physics is resonant in, and this is the blue peak on top of the smooth red continuous background. We're also going to assume that any potential signal is too small to be visible in the inclusive distribution, so we could not just be seeing it. And what we're going to do is we're going to split the data according to the value of the invariant mass into different regions. And we're always going to look at one region as the signal region and at neighboring regions as a sideband to do some interpolation tricks. And since in this construction, we kind of assume that we know where the signal is, in practice, we scan through different values of the signal region and just repeat the procedure each time. This gives us a trial factor by the number of signal regions, but this is not much different from traditional searches. In addition to this one resonant feature, we have in the construction I'm going to show now 4 additional features. So additional properties of the jets, like masses and the substructure. And in these features, we're not going to make any assumptions. We're just hoping the signal behaves differently than the background in some of them, but we're not going to decide a priori how it should look and in which of the features it should look different. 4 is a very small number, and I'll talk in a bit how we can increase this number of additional features, because of course, the more additional features we have access to, or the more features our anomaly detector has access to, the more chance it would have to catch an anomaly. Okay, but how do we actually construct this anomaly detection? For this, we now need to train a generative model. And what I mean with this is that we need some function that, let me read it off because that's a nice and concise way of putting it, that given a set of examples x, drawn from a distribution P of x, learns a mapping f, so that f of q of c is P of x for a random distribution Q of c. That sounds a bit complicated, but what this allows us is that if we assume this random distribution Q is a Gaussian distribution, and we train given a set of examples from the data, and this f of theta is a neural network, we can then sample from the multidimensional Gaussian distribution, pipe it through this neural network function f, and get new examples of data. And we're going to do that in the sideband to interpolate into the signal region. Now let's briefly discuss what type of neural network we're using here. So there is a large and very quickly growing body of different approaches for generative networks. There's generative adversarial networks, variational autoencoders, flow-based models, and diffusion models. And these things are being widely used in particle physics, specifically for different simulation tasks. Of course, they're also being widely used outside of particle physics for all these generative things and deepfakes and other productions. We're working a lot on using generative models to specifically simulate showers of particles in high resolution colorimeters. But if you want to hear about that, that's really a second talk all by itself. So you need to invite me again. Okay, What generative architecture are we using for the specific problem of anomaly detection? We're focusing on so-called flow-based architectures, typically normalizing flows. And for the experts, we're using masked autoregressive flow. The normalizing flow is a technique that maps from the data distribution to the latent space that should be a Gaussian distribution in an invertible way. So you see here the flow and the inverse flow are the exact inverse of each other. This is not a learned inversion. This is really a construction that makes these things exactly the inverse of each other. There's a few ways of constructing this. And secondly, it's constructed in such a way that the change in probability volume, so the Jacobian determinant of this transformation of going from X to C, is quite easy to calculate. You can think of this as structuring the function in such a way that the Jacobian determinant becomes a triangular matrix that is then very easy to calculate. And if we do this, we have something that's bijective and invertible and allows us to map from data to the latent space, and importantly in the generative phase, to map from the latent space to examples of data. And the normalizing flows, since we do have an exact accounting of the probability, we can just train this with the maximum likelihood learning objective. Okay, so we have the normalizing flow, and what we do is we train this generative model, this normalizing flow, conditional on M to describe the distributions of all these other 4 features, or how many other features we have. But in this case, it's a 4-dimensional generation that we then interpolate the mass value into the signal regions and produce new fake background examples in the signal region here. So you can think of this as a in situ background prediction model that is completely trained on data. So none of the construction I'm explaining here in the actual application has to be done on simulation. Of course, to understand the technique and to know what one is doing, testing this on simulation first is useful. But in the actual application, the generative model is fully trained on data, learns to interpolate the data, and produces these fake background examples in the signal region when we sample from it. Then comes the second step of the anomaly detector, which is to train a generative model that distinguishes between the output, to train a classifier that distinguishes between the output of the generative model, which by construction should be dominated by background-only examples, and between the actual data. And if the scenario is like in this nice picture, then the actual data should have an additional signal component, and the classifier should be able to tell these things apart. So if we cut high on the classifier value, we will enrich the data in signal-like examples. And we can look at the performance from a simulation-based study, looking at the significance improvement score, which is the ratio of the signal efficiency of a given cut divided by the square root of the background efficiency. You can think of this number as the enhancement factor that we apply to the Poissonian significance. The method I just described is called cathode, classifying anomalies through outer density estimation. And this is this nice magenta line. And it's the highest performing purely weakly supervised, so not making any assumptions about the shape apart from the digit resonance in this comparison. And if you look at the number here, this is an improvement factor in the significance of something like 12 to 15. Put very directly, if the data initially contains a signal with the 1 sigma significance, and we apply this technique, it would be a 12 to 15 sigma significance afterwards, which of course would be amazing. In practice, if we include something like uncertainties and additional statistical effects, that number becomes a bit smaller, but this is the general idea of this procedure. Okay, so this looks great. And potentially useful, but of course the question is always, does this work on data? And I'm now in the very lucky position that a couple of weeks ago, we, as the CMS collaboration, managed to publish a first result on this. This is a bunch of anomaly detection techniques. So I only explained cathode, but in the full paper, we actually train, test, and evaluate 6 anomaly detection approaches in parallel, and we applied them on the full run-2 dataset. So what do we see? The first study to briefly highlight is that we tested the actual expected gain in sensitivity by injecting different signals into the simulation. So it's essentially a constructed CMS owned toy dataset, where in addition to simulations, we inject a specific signal hypothesis, in this case, some particle X that decays to two-prong resonances. And on the vertical axis, we see the sensitivity of each of the anomaly detection techniques, so variational autoencoder, koala hunting, which you can think of as cathode without the sideband estimation, TNT, which trains pairs of jets against each other, two versions of cathode, and an anomaly detector that uses some signal examples to prepare a nice latent space. And we compare these different things also with non-machine learning based searches, so which is just an inclusive search in the invariant mass spectrum. This is the black line, and with two specific searches that also use substructure information. And the nice thing we see is that the amount of signal, so the injected signal cross-section that we need to cross the 3 sigma or 5 sigma discovery threshold is clearly lower for this bunch of anomaly detectors compared to the traditional techniques. Now, what we do next is we train cathode and of course all the other anomaly detectors on data. And I've not yet told you how we get from an anomaly score to an actual physically interpretable result. And we do this by training the generative model, training the classifier, then cutting on the classifier score of the events that are the 1% most anomalous in data. So just the 1% quantile of the classifier output. And then we look at the Diejet invariant mass spectrum after the selection. So this is the plot you're seeing here. This is the Diejet mass spectrum after selecting the 1% most anomalous events. The different vertical bars indicate different disjoint signal regions. This is why we have also some disjoint statistics in here. So this explains the gaps. And what we then do is we just perform a traditional bump hunt. So essentially assuming a signal mass bump shape and trying to see if fit to the background data shows us a deviation from this. And the answer is unfortunately that for cathode, but also for the other 6 anomaly detectors, all the local p-values of any excess are below 3 sigma. I think the largest one is 2.9. And overall, the data is very well described just by the smooth behavior of the background, even for this anomaly-enriched dataset. So this allows us to set limits, and I'm just jumping this page because that's the one I actually wanted to show. And this is the last interesting, well, there are many interesting aspects, but that's the last interesting point that I would like to highlight, is the question how we can actually produce limits for an anomaly detection technique, because the whole construction of the anomaly score and the analysis is done without a specific signal hypothesis. But if we want to communicate the result of the search to the world at large, to see what impact it has on our understanding of the models, in the case we did not find an anomaly, we need to know what model it excluded to what degree. And it's a very interesting situation because in principle, this analysis is sensitive to a large scale of possible beyond the standard model theories. We don't even know which theories it's sensitive to, but we need to check for each theory specifically what the sensitivity would have been to be able to produce an exclusion limit. And we do this and that's actually a computationally quite cumbersome part. We do this by explicitly injecting all of the signal models that we're testing into the data and then seeing at which threshold the classifier would have picked it up. And this allows us to test the sensitivity of this analysis to any of the possibly injectable signal models. And altogether in the search, we quote limits for 43 different signal scenarios at the mass range of 3 and 5 TeV. And these are these typical pictures. So each of these regions corresponds to one signal hypothesis, 2 plus 2 prong, 3 plus 3 prong, and so on. And each of these colorful confetti plots corresponds to the limit set by a specific anomaly detector. On the top, we have the actual upper limit. On the bottom, we have the improvement with respect to an inclusive search. And typically, we have something like between a 2% and a low integer factor improvement in the sensitivity gain by these anomaly detection techniques. So to wrap up the anomaly detection, we're able to do that on data. And now, brief discussion of what are the current limitations. And the first limitation that I already mentioned is that we only used a very small number of features per jet. And of course, it would be great if we could use more. And naively, you could say, okay, I just stick a couple of more features into my classifier. What could go wrong? Well, if we do this, and instead of sticking useful features into the classifier and just sticking a couple of purely Gaussian distributed random variables as extra inputs into the classifier, it turns out a lot can go wrong. So these different colored lines correspond to the classifier with extra Gaussian random noise inputs. And we already see that if we go from 2 to 5 extra features, the performance drops quite radically. This is because this weakly supervised anomaly detection is a very hard learning problem where we distinguish between two data sets that are very similar, both are mostly background, and one has a small signal on top. Turns out boosted decision trees, hist gradient boosting specifically, are much more robust against such noisy features, and they allow us to use much more inputs. So we go from the baseline, which was these 4 features that we discussed before, to extended set 3, which had something like 50 features, different chat substructure variables, which gives us another round factor of 2 significance improvement score. We can even push this one step further and use full low-level, essentially particle-level inputs by using the latest developments in generative models and replacing the classifier with a transformer. This gives us a maximum significance improvement of a factor of 50, which is amazing. Although the performance at the low end of the spectrum, so at the amount where there's low amount of signal, still needs to be improved. But in principle, this works as well. And we can even expand this to cases where we have the anomaly not as a peak, but in the tail of some distribution as produced by missing energy. The downside of this is this cannot be done without a background template that we would need to get from simulation, but one still can construct such things, extending the anomaly detection to the non-resonant case. And the last thing to think about is what could we do if the events that we record are even weirder? So if we have anything going on there. And there's a second school of anomaly detection techniques that are called autoencoders. They're quite simple. They try to learn to map the data back to itself. So we have an encoder that maps the data to a latent space. This is a lossy compression. And then we have a decoder that tries to map from this compressed representation of the image back to the image itself. And we can use the loss function, so just the difference between the input and the decoder applied to the encoder of the image, as a quantifier for the anomalousness, because if something has never been seen in the training phase, it will be badly reconstructed after being compressed by this encoder. And we can see the loss curve here for the top tagging problem, for example. And the nice thing is now inside the CMS collaboration in the test board of the level 1 trigger, there's a similar version of this, not exactly that architecture. It's actually a variational autoencoder used as a first strategy to see if we can trigger on anomalies without making additional examples. And this is one of the events that recorded that was not picked up by any other trigger. But of course, you see, this is mostly really just detector noise. Okay, we're at almost 45. So if I can have 2 to 3 more minutes, I think we can wrap this up nicely. And the first takeaway is that, of course, searches for new physics have come a long way since the 80s, and anomaly detection is, in my eyes, very exciting strategy to enhance possible signals, maybe even by orders of magnitude, without specifically knowing what to look for. This was constructed first in the context of resonant anomalous searches, so still assuming decay into pair of jets, but essentially we're pushing now on all the boundaries to make this more flexible, and people are also deploying it on experimental data. So it's a very exciting direction. And just to close off, one last point, because all these machine learning approaches are very data and compute hungry, and there is a new development coming from large language models. And we've already seen an example of this development before, where we observed that the fine-tuned party that used 100 million training examples was much better than the party algorithm trained just on the 2 million examples. And we can push this idea one step further by thinking about whether we can train a joint backbone model. So essentially an architecture that is trained on a number of different classification, generation, and other tasks at the same time. And that then just has a small second part of the network, a so-called task-specific head that is fine-tuned for the specific problem one tries to solve. We've experimented with this using an architecture that is very much inspired by large language models, so essentially a GPT-like architecture using a transformer backbone after transforming chats into tokens, so really into integer lists of particles. And the one nice result that we can show with this is if we pre-train this model on the generative task, so learning to produce chats without telling it anything about the identity of the specific chats it's producing, so using data that is very cheap to get, and that could even be done experimentally, and then fine-tuning it, so just adapting it to the classification task, we see the classifier is something like 10, is like something like 100 to 1,000 better in terms of the amount of training examples it needs to reach to get to the same performance, although the overall accuracy is still very low. This, I'm really at the end. I don't need to read it off. Thank you very much for your attention, and of course, I'm happy to take any questions and discuss.
Thanks a lot, Gregor, for this funny talk, also with the Godzilla. I have a few questions, but I want to ask the audience if there are any questions for Gregor. Please raise your hand or speak up.
Yes, I do have a question.
Tesio, go ahead, please.
Yeah. So first, very nice talk. Thanks. And very funny the Godzilla part. I laughed a lot. But regarding this anomaly detection, if I understand correctly, you can basically get rid of the estimation of the backgrounds because you are using directly the data. So
no, unfortunately not. That would be great, but we can't do that. So this was the part, how should I say? That's the part that uses a bit less machine learning, so I don't talk about it that much, but the key point is, here we go. So what we do is we have this in situ background estimation that learns, let's say, the correlation in any of the features that we put in. And then we train a classifier between the data and this in situ estimated background. This is all constructed on data. And what we do next is cut on the 1% tail of this distribution. And this gives us a new mass distribution. And in the end, the statistical test we run on this is really just a bump hunt. A bump hunt means that we do a background estimation, but this background estimation is just a fit. So we fit a falling, I don't know, some falling exponential distribution to the data.
Based on only on this 1% selected data?
Exactly. Fit? So we, sorry? Exactly. So essentially this whole business of cathode and the other anomaly detectors is there to enrich the data in potential anomalies. And then the analysis, and then let's say the statistical analysis we do on top of that is a relatively simple bump hunt in one dimension, namely in the invariant mass. So the only background estimation, the way we usually think about it, is the interpolation in the mass spectrum. Of course, we also have the background estimation that is done by the generative models. And the bump hunt is a relatively simple approach here. There is a very nice body of work by Andrea Wulzer et al., going under the name of Learning New Physics from an Imperfect Machine, that focuses a bit less on the, let's say, learning the background from data, and that has some nice results on improving the statistical side of these things.
Okay, I see. Thanks.
Thanks. I have a question, Gregor, concerning this anomaly detection. So basically, you are defining the signal based on the invariant mass distribution of these two jets, correct?
Let's see where this goes. I have a bit of a stomachache if you say defining the signal, because in a sense, there's two steps that define the signal. The one step is the fit in the invariant mass distribution, but there's also the earlier step of the classifier that is learned from data. And these two things together define what we see as a signal.
Okay, but in principle, you could have chosen not the invariant mass distribution of these two jets, but perhaps other observable to use in the signal definition.
Absolutely.
Or that doesn't mean that is, or if you do that, does that mean that it no longer becomes a bump hunt search? So then you cannot apply your methodology.
Yes, exactly. Okay, exactly. That's one of the frontiers I briefly where are we in the slides? That's one of the frontiers that I briefly touched on. So there is two kind of generalizations that you could think of. The first generalization is that you say, okay, we look specifically at the mass of the dijet system. Now, it would be much nicer if we look at the 3-jet, 4-jet, 5-jet mass and the jet plus lepton mass, blah, 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 but all of them still being invariant masses. This could be done. The problem is that each of these new distributions, in principle, would be its own analysis, and figuring out how to combine something that looks at all possible mass distributions in one analysis is, I think, needed first before we go out and do 10 different versions of the same search, just looking at different distributions, because that's not very efficient.
Okay, I see.
Now,
so basically your BSN physics can basically be anything, but then you will need to do like a more complex network of networks to kind of...
You need to figure out a better way to deal with the mass. The second step that would be even more interesting in a sense is if you say it doesn't need to be an invariant mass, it doesn't need to be a spectrum where we assume the signal is a resonance, but where we assume the signal is on the tail. Now the problem is the whole statistical part only works because we can do a bump hunt where we fix the background distribution from the sidebands and we just do a nice fit. As we all know, extrapolation is very difficult. So if we stop assuming that the signal is a resonance, but we assume it's in some tail, then this doesn't work anymore. And this is the part, this is the part I said here. We can build constructions where we have the signal on the tail of some distribution. So we looked into the signal living on the tail of the missing energy, and we use a classifier very similar to cathode to enhance the tail of this the signal that lives in the tail. But the extra ingredient we need to do that is some assumption of how the background behaves in the signal region, or at least close to the signal region that we can extrapolate it from. So either taken from simulation or taken from a control sample. And then we replace the bump hunt style statistics with an ABCD style background estimation. So essentially, what we construct here is a classifier that is decorrelated automatically from the missing energy. So the classifier and the missing energy are not correlated. If they're not correlated, we can do ABCD background estimation, and we get again the background count in region A, which is the one extension of this method, or the one direction of extension that goes beyond just assuming invariant masses.
Okay, I see. And in principle, instead of missing energy, could you have something more weird? Like I'm thinking long-lived particle, exotic signatures.
Okay, long-lived particles are great. You could, in principle, put anything except missing energy here. Since we don't assume it's resonant anymore, you really don't care. You can live with anything. But for long-lived particles, I think the thing I said right before is actually quite relevant. So if you have long-lived particles that decay into some crazy stuff, but that are maybe still resonant in some variable, then the thing you care about is using the long-livedness of enhancing a possible peak of this. And this is exactly why we look into replacing these 4 high-level features, so just the masses and the substructure, with essentially all the particles in the jet. And when I say all the particles, I mean all the particle flow candidates, including their displacement information, including any secondary vertex information, and so on. So any long-lived particle or anything like an emerging jet and so on, as long as it's produced by something that it has a resonant invariant mass in, the long-livedness could be captured by these particle type inputs. But of course, if you can't find something where it's resonant in, then we need to go to this second stream of ideas. But as soon as there's something where the new physics is resonant, then it just becomes a question of making sure that you can enhance this resonance by the other features.
Thanks. Any more questions?
Hi, yes, this is Francisca. Hi, Gregor. Thanks for the talk.
Hello.
And this is maybe a super naive question, but this anomaly detection has been done with another than jets in the final states or not?
Good question. There is 2 results by Atlas, one using a slightly simpler version. So that was called Koala. I mentioned it before. It was the first weakly supervised technique, and it uses it does not use this more elaborate sideband estimation. And there's one result using autoencoders, but both of them were still done with jets. So there's a few different, there's 2 papers by Atlas out that also do anomaly detection, but this and the Atlas papers all use jets.
Okay, but do you know if there any physics reason why you use jets, or it's just that because nobody has done this with another particle at the end?
Well, I mean, I think it's like a conjoined physics and sociology reason. There is lots of machine learning done work for jets and jet taggers because especially hadronic resonances have a very rich background. So people work on machine learning for jets, and of course, then this is a natural particle to also use in the BSM search. In principle, we discussed this earlier this week when I gave this a similar version of this talk in Mainz. You could do it in the diphoton final state with very little modifications. So the thing to figure out is maybe the features to use, and that's where it becomes more difficult because maybe jet tagging is a bit more often worked on than something like photon or tau tagging. But in principle, you can replace jet with any particle you would like.
Okay. Good, thank you. It's just
it's
curious.
It has not so widely been done yet because jets are like the obvious thing to play with, but there is no real limitation.
Okay, thank you.
Thank you.
Gregor, I have a more broad question also concerning the autoencoders. So I understand that the motivation behind anomaly detection and autoencoders is to be very model agnostic in the new physics search. Of course, that is very hard because you still need to kind of define your signal somehow or your signal region, etc. So how do you see the applications of these tools? So what would be like what would be ideal for you? Like, for example, seeing an anomaly with these methods, or that there is new physics perhaps, or a statistical significance. We've seen some other anomalies, some resonances, some very low significant, I don't know, bumps in the past, for example, the diphoton, etc. Could this tell you anything about the underlying model that produced the anomaly? I'm not sure if you understand my question. It's like, what's your philosophy?
Let me try to answer, and then we'll see if this goes in the right direction. So, well, if you ask me what I want, of course, I want to run an improved version on anomaly detection on the run, maybe still again on the run 2 dataset. It tells me where the new physics is, and then I go and redo that analysis, specifically looking for a specific signature on the run 3 dataset, and we find it. And since anomaly detection does not rely on theorists, maybe this time the experiments get the Nobel Prize. But to your question, whether we could know what we're seeing, yes. So we've done a toy study where one of our students injected a signal into the data, and then we tried to figure out what signal was there. And it's shockingly easy, because what you can do is you can look at the distribution of all the input features, but also of all the other features that you can reconstruct. Once you have your 1% signal-like selection, you just calculate any feature that you care about for this 1% signal-like events, and then you compare this distribution to the overall distribution, to the distribution of, let's say, the 100% of the data. And that immediately tells you what features and what regions of the features the anomaly detector used to pick out the signal. So if you look at the histograms, for example, we could immediately see it was something like a 3-prong and a 2-prong resonance, one with the beachhead, and we knew the invariant masses just by looking at the histograms for 5 minutes. So if this discovers an anomaly, it's very easy to pinpoint what it has seen. It doesn't tell you the underlying physics model. Of course, if it's a 3-prong and a 2-prong, blah, 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 you can still write different Lagrangians that produce it, but it narrows it down considerably.
Mm-hmm. Mm-hmm. Okay, this is very good. So what I'm thinking, if it's like, if we see something, are these models like ready to understand what that really means for BSM physics? And
yes, I think
they are ready.
Yes, if we see something, we can very easily turn that around into a statement of there is new physics in the 3-2 space, in this phase space, and any theory that produces it should look at it. It's also it's this interesting aspect of anomaly detection that we can very easily say there's a global p-value or not, but then we need to rerun for each specific signal that we can inject. But of course, we could imagine if we see something, we just inject and fine-tune different signals until we get the best fit to the data. So we could, in principle, fit the properties of the signal from the data. So yes, if we see something, figuring out what we've seen is actually not the hardest problem. It's more the statistical game of seeing something first.
Okay, great, thank you. Final questions or comments for Gregor? Well, I guess not. If not, Gregor, we thank you again so much for this wonderful talk. And I hope you can rest now from your cycle. Thank you
very much for the invitation. It was a great joy. Very nice discussion. Have a nice Friday and also a nice weekend very soon.
Thank you. And thanks everybody for joining, and see you again on our next Saphir webinar. Ciao, ciao. Bye.
Bye.
Thank you. Bye-bye.
Bye-bye. Thanks.